suggests a fix for a library that's got like, that it thinks like, that has seen on GitHub a lot, and now in your company you're not using that library. So now it will give you a fix that it thinks is right, but it's not good for you. So you have to be kind of very careful with this stuff. Okay, so this is a good question. So I don't think like I'm very careful never to mention the word AI. It's machine learning, right? It's like it has nothing to do with intelligence. It knows whatever you train it on, but it's not kind of creative. What is it, Michael? Like unlike Michael, right? Michael is like actually like like, are you artificially intelligent? Are you a robot, or are you like a human?
I'm trying to influence you to stop your presentation because you should start your presentation.
All right, sounds good.
That's. I'm sorry, Henrik. Your question is down the drain. Oh, right. Hello, everybody. My name is Michael. I'm running Focafé together with Ellie here in Stockholm, and super great to see you here, and Erik. Yeah, Erik should have been here in the spring. That.
Oh my goodness!
Yeah. And we planned it. I think it was a year ago. We planned it. Yeah, I will be in Sweden in the spring, so I could do a talk at Focafé Stockholm. Awesome. And then we came into April, May, and then Erik sent all the information as you should. Yeah, everything worked out fine. And I posted the event on our website, and I asked Erik to check it out. And he said, it looks good, but it's the wrong city. I can't be in Stockholm because my plans is, I thought it was Malmö, and yeah. And then he saw that he made a mistake, and he said, all right, in that case, I will come back to Stockholm in the fall. And the funny thing, the rest of the story is quite funny, because just a few months ago, or 1 month ago, something like that, Cecilia from Factor 10 asked me, could we do an event in Stockholm with Erik Meijer? So yeah, of course. So they had, so Jimmy Nilsson, the CEO of Factor 10, he talked to Erik asked Erik to do a talk at Focafé Stockholm. And Erik said, yeah, of course, super, that was not a hard question. No, that's quite simple. So, here he is, and I'm really happy to see you again.
Thank you.
Fabulous. And so the only thing I should do now, the rest is I should just check how many of you would like to eat after the talk. No, no, I take it the opposite. How many of you does not want to eat anything at all? All right, 7, I don't want to eat anything. Okay, we will have quesadillas. Maybe you changed your mind? No, no, okay. And how many of you are vegans? 1 vegan. How many are you gluten intolerant? 1. All right, okay. And then we will have a mix of vegetarian and meat. Right, that's what I should say. And yeah, I also have another surprise for Erik today, that we have Tanya here from Ukraine, who is running a startup. Tanya, come. Tanya is running a startup, a young startup. It's called Events Terminal, and she is doing the live stream of this event through her new platform. And of course, Focafé is also a startup, and we support also other startups. And we did the same thing yesterday in Malmö. So this is the second time they're running a live stream. So
yesterday people for more than 20 countries joined to watch event at Focafé.
Yeah. So we'll hand up with a cool startup. Thank you, Tanya. And now, Jimmy, you have to say some words. Our sponsor tonight.
Yeah, I realize you're not here to listen to me, but to listen to Erik. But 20 countries. I hope for 40 at least tonight, right? So I'm Jimmy Nilsson from Factor 10. And we love Food Cafe, of course, not just because of Michael, but because all the things you're doing, supporting good stuff. Factor 10 also would like to help making the world better, but you are doing it maybe more. We have to fight about that. That's right. Yeah. One way we are doing, trying our best to help the world become better is by sharing what we learn and talk about that. So when Erik said that he was coming to Sweden, I said, well, why not go to Food Cafe? They're talking about Gutenberg upstairs. Who's that compared to Erik Meijer? So please get started. Welcome.
All right, thank you. So yeah, so what I want to get, talk to you about tonight is a little slice of deep learning. And we just had elections in the US, so I have a couple of quotes from famous presidents, and one of them, Abraham here, is science should simplify, not complicate. So what I'm going to explain to you tonight, after the talk, you should feel that everything I said was trivial. Okay, if you feel like that, then I've done my job. If it doesn't sound trivial, then I've not done my job. All right, so I'm going to take this concept and really boil it down to the simple essence, and hopefully you will agree afterwards that it is in fact trivial. So a little bit of history. When I was an academic, long time ago, I was teaching software engineering. I don't know if people here ever read Somerville, the software engineering book. I was teaching this from the first edition. And when I was doing that, I felt like a vegetarian butcher. So I felt I'm teaching these students how to do large-scale development, but I have no clue how that works. I never did it myself, so I cannot teach this thing and look at myself in the mirror seriously. So that's where I quit academia and went to industry. And maybe fortunately, I don't know for me, but every place where I've worked at, and maybe it's the self-selecting bias, this was the main software engineering principle that we applied. And again, it's another quote from a famous president, working software over following a plan. So everything in software engineering you can forget. It's all about creating working software, right? And what that means is that software is the currency. Software is what it's all about, or code is what it's all about, right? And then, how do you create code? Well, you author it, you generate it, you search for it, you synthesize it. And then when you have code, you edit it and you refactor it, and then you get ultimately, of course, the goal of code is to run it in production. So you have to deploy and save it in source control that you can find it back. But here's the question. It's after so many years, 50 years ago, there was a famous conference where the word software engineering was invented, and also the word software crisis. But again, the fact that there's so many people here tonight shows that we don't know how to write software yet, which is kind of embarrassing, right? 50 years we've been studying this, 15 years we've been writing code, and still we're scratching our heads, we don't know how to write software. So maybe it's time that humans stop writing software and we leave it to the machines, because we as humans are maybe not smart enough to write software. So that's what I decided to do. It's okay, I accept I'm just a human, I'm stupid, I'm not going to try to write software anymore. Can we teach the machines to do it for us? And again, if you look anywhere else in the real world, machines are doing the work for us. We're not digging holes by hand. No, we have a machine do it for us, and et cetera, et cetera. So that's what we're going to do. Okay? And of course, I'm not the only one that wants to do this. This is what people call software 2.0. So everybody here is probably still doing software 1.0, where humans write the software. In software 2.0, it's the machines that write the software. All right. This, by the way, is an interesting blog post that you should read. So what's the difference in, like, really concisely expressed between software 1.0 and software 2.0? Software 1.0, there's a human that takes coffee and turns that into code, or beer, or wine, or like chips, peanuts, whatever more do I see. In this new world, you take data, training data, you pass it into some magical machine learning algorithm, and out comes a model. Now, what's the difference between model and code? So I think the machine learning people like to use expensive words, and the whole point of this talk is to kind of like show that all these expensive words are kind of like trivial. Remember that? But there's a big difference between model and code. You can say model is just code, but there's one difference. Machine learning people are less arrogant than programmers. They kind of like acknowledge that these models don't compute precise results. They predict a result. Where if we write a function and we say it's a function from end to end, we kind of promise a lot of things. We're over-promise, but we under-deliver. Because this function might have bugs, it might throw exceptions, it might fail. And when you look at the model, it just says, oh, this is here's a picture. This is a cat with 80% probability and a dog with 10% probability and a glass of red wine with like 2% probability. So it's just honest about the fact that it's just guessing. And I think this is a good thing in general. So I think even in software 1.0, we should be like less arrogant and say, yes, these things might go wrong, or we're just guessing. And I think that's what probabilistic programming is a good thing for, because there you can return probability distributions that can express the uncertainty or the certainty about the results. So this is a big kind of difference. The other difference is that the new currency, or what people say, that data is the new currency, or data is the new oil, right? So data is what drives the machine learning. So how do you get the data? Well, you get that from tracing or monitoring or other things. And then just like you have to refactor your code to clean it up, you have to clean up your data. And then once you have your data, you can use it to train your model or to visualize it or do other things with it. And some people say that, like, this part here is like 99% of the work, and maybe the cleaning is like, 80% of the work. And so there's still like, a lot of like human work involved. But ultimately, once we have that data, we can train these models. So it's really the magic is in that training data, because the machine learning model cannot. It's like, again, like we talked a little bit about this before. I don't believe in artificial intelligence. These things are not intelligence. They just get like generalized from the data that you feed to it. Maybe other people believe in AI. It's not me. It's a useful tool where I can have the machines generate models for me, but I don't pretend that it's intelligent. Here is a example. This is the hello world of machine learning. It takes flowers with some features, characteristics of these flowers, and then it tries to predict what flower it is. Now, again, it tries to predict what flower it is. So this is like this bar chart here is a probability distribution. So for this flower, it thinks like, that is whatever, Setosa, I don't know. But you see that it thinks it's that one, and maybe you got like, with a lower probabilities, one of the other ones. And then for the second flower, it thinks that's like pretty sure that it's this one. And for the last one, it's kind of like, yeah, okay, I think it's that one, but these other ones are also kind of possible. Okay, so this is the big difference between, like, a regular programmer would say, oh, I'm so smart, I know exactly that it's this flower, and you don't express the certainty or uncertainty. So I think this is one of the things, like, if you forget everything I say today, this is one thing that we can learn from machine learning, is that, think in terms of your answers as being uncertain, right? and so express that. So you should never kind of like claim an overpromise, like I'm going to give you a precise answer when it's not precise. Now the other thing is that if I would give you 10 million Swedish kroner to write a program like this that can recognize flowers based on some features in the traditional way, you couldn't write that. Even Jimmy's 10x developers, you know, cannot do that, right? Even if they're 100x smarter, they cannot do that. You cannot beat machine learning with these things, right? Everybody uses their smartphones, like, you know, whenever you take a picture and it shows, like, you know, little squares over people's heads, that's using machine learning. You cannot beat that with traditional algorithms. So there's a whole bunch of things that even if you don't believe in machine learning, there's a whole bunch of algorithms or applications that you can access in this new world, in the software 2.0 world, that you couldn't do in the traditional world. So that's another reason to look at machine learning. And even if you're skeptical about it, it just opens up a whole bunch of things that we couldn't do before. And that's, for me, the main reason that I'm interested. So here's another example, recognizing cats and dogs, which is obviously super important, right? We all know that we cannot live without that. And as I said, like, you know, even though software engineering is 50 years old, we don't know how to write programs like that. So how do we do it? How do we write programs like that? Well, let's look how we do that. So this is the high-level explanation of what machine learning does. So you can, like, you know, you write your model here, which really is a composition of functions. And the machine learning people, and when I say machine learning here, I typically mean deep learning. They say, oh, it's like, you know, I have a bunch of layers. These layers are just functions. And if you stick two layers together, you're doing function composition. So what you're writing, the model that you write, is a composition of functions that is parameterized by weights. And now what you're trying to do is you're feeding the input to this function, and out comes a guess, because that's what this the machine learning algorithm does. You look at the output that you get from your training data, and then you're applying a loss function that kind of compares how far these two answers are, what the difference is in these answers. And that's the error. And then what you do is, like, you apply some high school mathematics. Like we all know from high school. Oh, is this me or is this? Oh, it's the ventilation. I thought it was, like, you know, like the feedback. But the ventilation, that's a great sound for ventilation. It's like a rock stadium. Yep. But we all know from high school, if you want to get, like, you know, minimize a function, right? Say that you just have a simple quadratic function. How do you minimize that? Well, you you take the derivative and you look where the derivative is 0. Okay, so what do we do here? We take the derivative of the loss function here, and we look, is it kept, like, you know, if it's positive, it means we have to move a little bit to the left. If it's negative, we have to move a little bit to the right. So that's what we're doing here. We're kind of updating these weights, and we're rinsing and repeating that until we got, like, you know, set these values. So here's some actual code that shows kind of like what you actually have to do. And again, this is the hello world of machine learning. Here is the, like, you know, the training data. You have to get, like, specify your weights. Here is the model. And again, like, you know, these are, I'm not going to get, like, explain this. You're just got, like, putting together usually some standard layers with some transfer functions and whatever. And then what you need to do is you need to map your discrete values, in this case flowers, to a kind of like continuous input. And this is, like, you know, I think one of the still open issues in machine learning, because since these, I should go back to here, why I'm interested in differentiable programming, because in order to get, like, you know, be able to get, like, you know, up these weights based on the derivative, taking the derivative here, these functions have to be differentiable. So what we're trying to do is we're trying to define a programming language in which we can write that yellow box, where every function, and these are functions, these are really pure functions. So if functional programming wins, it is because, you know, it's used in deep learning, not because people are using Scala or Haskell or whatever. No, this is where functional programming is useful. But we want this functional programming, or functional program, where every program that you write is differentiable, such that you can plug here in arbitrary, like, you know, an arbitrary function as long as it's differentiable. So this is what, like, you know, what people like, you know, mean when they talk about differentiable programming, is that you can, instead of having like just layers, I can put much more complicated things in that yellow box. But you still now have to map from your discrete space into this continuous space. And the problem of embedding is really hard. In this case, it's simple because all these values are kind of like, you know, already kind of like, you know, floating point numbers. But in general, people do kind of like all kind of crazy tricks to map from discrete space into continuous space. In some sense, that's not a new thing, because we have the same thing with databases, right? This is called the impedance mismatch. If you have a relational database and you have your Java objects, now you have something that has hierarchy and inheritance, and here you have something that has flat tables, and people have figured out over the years how to do these mappings. There's patterns. Here we're not yet that far, but I'm pretty sure that over time we will kind of have best practices how to map complicated things into this continuous space. But this is something where there's the dot dot dots. This is something you have to define. All right, so let's just assume that we know how to get, like, you know, do all the mechanics here where we just adjust the weights. And what I want to get, like, you know, focus on in this talk is how can we get, like, differentiate arbitrary code, or how can we get, like, you know, make sure that if we write a function that is differentiable. And if you get, like, you know, do a little Google search for this, you find like a lot of explanations for this, but these are really complicated. Okay, so they use like expensive words like strict, symmetrical, monoidal categories. Like, okay, like I'm already like, you know, I need like they don't have anything stronger here, but when I see this, like, I need something stronger. Or here it's like, you know, again, like the simple essence of automatic differentiation. Oh, that also uses category theory. And here's like automatic differentiation in machine learning. Oh, this talks about Jacobians, and look at all these Greek letters, and like, you know, like I don't even know how to type this on my keyboard, and like how do I put a dot on top of something, boldface? It's just all too complicated, right? So can we explain this without any math, with only high school math or even elementary school math? So that's my claim. You don't need any of this, okay? So what is the real essence of automatic differentiation? Because my brain is the size of a peanut, and there's a whole bowl of peanuts. Can you pass that bowl of peanuts there? So these are peanuts. This is the size of my brain. So just to make sure. So it has to be simple, because otherwise it just doesn't fit. There's not many neurons that fit in this like, you know, little volume. Okay, so let's make it really simple. And hopefully what you will agree with me afterwards is that it's like a dog, right? You have this beautiful dog. It looks very impressive. You put the garden hose at it, and then underneath there's a really simple, skinny dog that's not at all kind of scary. And this is the same thing here. So you look at this stuff, and you think, oh, like, do I really need to understand all this? No, you don't. So let's put the garden hose on all this stuff and see how easy it is. This is all the math that you need. Okay? This was invented by William Clifford in somewhere like, you know, 100 years ago, 200 years ago. I cannot even do simple arithmetic. So everybody knows complex numbers, right? You remember complex numbers from math? If you're doing graphics, you're probably using complex numbers all the time. So complex number is a plus bi, where I squared equals -1. Yep, remember that? Then you think, why I squared equals -1? Isn't that weird? Sure, but it's okay, right? You can just take it. But why can't we just take another? Like, why can't we define I squared to be +1 or 0? So let's do that. So a dual number is like a complex number, but instead of I squared equals -1, we say I squared equals 0. And in order to kind of distinguish between complex numbers with I and dual numbers, we just use a different symbol. So we use epsilon instead of I. Okay? So a dual number is like a complex number, except I square epsilon square equals 0. Now, that choice is really remarkable, because if you do that, this follows. If you have a function f and you apply it to one of those dual numbers, what it computes, it computes f of a plus the derivative of f of a times b epsilon. And again, this is like a magical property. Don't care like how this works, we will profit from it, right? We'll just take it. Just if this is the case, I'll take it, right? Now, if you want to understand why this is the case, you have to look a little bit deeper, and you have to look at Taylor expansion. Maybe you remember Taylor expansion, Taylor series from math. This is really remarkable, right? Somebody in, like, Mr. Taylor in 1715, I don't know how you can come up with this, but he kind of said, like, if you give me a function, you can forget a little bit about the a. If you give me a function f, I can write that as this infinite sequence, this infinite sum that involves factorials and the nth derivatives and like exponentials. It's just mind-blowing. So this is the mind-blowing math that's behind this. But again, like from this, you can show here that when you take epsilon squared equals 0, that if you apply a function to a dual number, it will give you the function plus the derivative. All right? And this is all the math that we will use tonight, plus some regular functional programming tricks. Okay, so that looks much less scary than all this category theory, strict monoidal categories. It's just like simple math from 1715. I mean, how, like, they, I don't know, probably Stockholm, or they already built like beautiful homes back then. Anyway, if you look at this thing, that if you take a function on numbers and you lift it to work on dual numbers, and that's that thing is a functor. So, but again, I promise that I won't use expensive words tonight, so you can forget that. But I thought there were a couple of, like, somebody told me, oh, I learned monads from you. I think it was you. Well, here's like, this is a functor. But that's all kind of like, expensive stuff that I will do tonight, just for you. Okay? Now you can go home and say, I know that dual numbers are, like lifting into dual numbers is a functor. That may impress your colleagues at work tomorrow. Now, let's simplify it even further, right? Because just this a plus b epsilon, that's really just a complicated way of writing a pair. So let's just write it as a pair and then show the math. So if I have two of these pairs and I add them up, what I do is I just add up these guys and I take the derivative of these things, and that's it. If you multiply two of these pairs, you get this here. And if you look in Wikipedia for the product rule of differentiation, that's what you find. This is the product rule of differentiation, and it follows directly from dual numbers. And then again, remember, this was the property that we get, like, that we're interested in. And there's no epsilon here because we're just doing pairs here. Notice that we don't need the chain rule. I don't mention the chain rule. I don't know if you remember the chain rule. That's something I can never recall. I always have to go to Wikipedia to look at how the chain rule works. But you don't need it, as I promised. This is the only math you need. If you do it, this follows from that. All right, so let's write it in code. So we I showed it in handwriting. Now let's write in code. So here's some Scala that implements dual numbers, and it's exactly as I promised you. It's just a pair of the real part and the epsilon part. And then you define addition, multiplication, just for fun. I also define division and sine and cosine. And then here's an implicit conversion from doubles to dual numbers. And that's all. So here you have automatic differentiation in, what is it, 10 lines of code? How hard is this? Right? No category theory. Yes, it's a functor, but you know, it's only relevant for you. All the rest is like, what is a functor? It's really easy. So life is sweet. This is math from 1715. So let's look at some examples. So here's you know, a function. It's like x squared plus 2x plus 3. We can take the derivative of that. Here's a more complicated function that uses assignments and loops and everything. It computes the sine function using Taylor expansion. Doesn't matter if this thing takes a dual number and returns a dual number. I can take the derivative because that's what dual numbers compute. And then here, this thing computes x times x times x times x times x times x. It's like, you know, as a graph. So it's kind of sharing. And that works as well. If I run that, you see that thanks to the magic of the JVM, this should be linear, but thanks to the magic of JVM, the longer this thing is, the faster it goes. Isn't that amazing? These modern machines are awesome, right? It's like, you know, instead of like performance going like this, it goes like this. I don't know why it works, but you know, like I'll take it. So I think here's probably got like, you know, switching from like, you know, one generation to the other. I don't know what happens, but this is why people prefer C++ over a garbage collected language. Because like in C++ you have like a predictable curve instead of like all these spikes that your garbage collector like messes you up. Which is also strange, right? It's like 2018 and we still have not built the predictable garbage collectors. And you get strange graphs like this. All right, now, of course, I also want to kind of take derivatives of functions with multiple arguments, because if you remember the very simple neural net that I showed you had multiple weights. So, and all these weights are, I want to take the derivatives with respect to all these weights. So I need to take derivative of what people call multivariate functions. So you can go tomorrow, if you can, like, you know, go back to work, and if you write a method that has more than one argument, you can tell your colleagues, I just wrote a multivariate method. That will impress your boss, right? It's like, you know, yes, he learned something or she learned something at Fou Café. What multivariate methods are. I mean, this is super useful information, right? So try to introduce this terminology at work. It's much better than Scrum or anything, just multivariate methods. I mean, that sounds impressive, right? Like you're really doing something. But it's just a function with more than one argument. And the way we do it here is we just use a map, a hash table from names to values. It's like, you know, I have a different epsilon for each parameter, and then all the math here still looks the same, and all I have to do is I have to overload plus and multiplication over these maps. And as the grumpy cat says, if you look at that code, it's just a kind of complicated way to do pointwise addition and pointwise multiplication. So it looks simple enough, right? Should all work? Let's check. What we have done now is we have made all these operations. So even though, like here, this overloaded code looks really simple, right? I still use addition and multiplication here, but these are now linear operations because they take these maps. So even though it looks just like you're doing addition of n things, and so you're combining two maps of length n, which is linear in the length of the number of variables. And if you now construct an example that kind of like, you know, adds up a lot of these things. Now you start with maybe with like, you know, map of length 1, but after the next operation you have a map of length 2 and then a map of length 3. So it means that you kept like, you know, the total runtime of your program will be 1 plus 2 plus 3 plus 4. And then again, like Mr. Gauss, somewhere like 200 years ago, said, that's quadratic. So by just doing this simple change, that doesn't look like much, right? Because the code still looks the same. Suddenly, our algorithm has become quadratic. And can we prove that? Well, let's see. Let's write a simple function that just takes n variables that I want to take the derivatives of and just add them up. So this looks a little bit complicated because I use a fold left. Yes? Fold lefts are great, right? So I want to show off that I still know some functional programming, right? I know what fold left is. So you take a list of variables that you want to take the derivatives of, you add them up from left to right, and guess what? You see that it becomes quadratic. And the JVM loves quadratic functions. Look how smooth it is, right? There's no spikes anymore. The garbage collector is now peaceful. It's like Zen. It's like, look at this. It's, like, it's still a little bit like, you know, but it's already much flatter. So yes. So if you want your garbage collector to be predictable, write quadratic code, but really don't do that because it's like super slow. Now, I'm not the first person that thought that they did something cool and then turned out to be introducing quadratic slowdown. There's this blog post here, or series of blog posts, accidentally quadratic. This is another thing you should check out tonight or tomorrow or doing work. It gives you a lot of real-world examples where people kept like, you know, made a small change and suddenly like, you know, the algorithms were quadratic. And they have like a lot of examples from real systems. And probably, I think everybody here in this room probably had this, right? Oh, I make this little change and suddenly, oops, it's quadratic because I have this kind of like, you know, this effect where you're just kind of like doing one thing and then two things and you're adding them up. So how can we get like, should we all go home now and say it's like, yeah, Erik was lying. He said like this automatic differentiation was so great and so easy, but quadratic, that's not acceptable. So can we fix this? Well, the answer is yes. And the answer is yes, because this thing happened too in functional programming. So here is like, you know, how you define lists in Scala. So it's like empty list or like the cons of a head and a tail. And if you define reverse of a list, and you use reverse, you define reverse using list concatenation, it's well known that this is quadratic. So I don't think that like, you know, the JVM garbage collector, like I said, like it likes quadratic functions, but it doesn't like pure quadratic functions. Like if you write functional code, it's still kind of like, it's still agitated. It's like, but you still see that it's quadratic, right? So list concatenation is linear time operation. And if you get like, you know, analyze what's going on here, it's exactly the same thing. You're just concatenating one thing, then you're concatenating two things, you're concatenating three things. So you're doing a quadratic amount of work. But people with brains much bigger than a peanut knew how to solve this. So what you do, this is from 1986, John Hughes, is what you do is you represent lists by functions. Now, concatenation of lists becomes function composition, which is constant time, and now reverse suddenly becomes linear. So this is like magic, right? If you represent lists by functions, now suddenly, magically, reversing a list becomes linear instead of quadratic. That's a trick I will take anytime. All right. So now the question is, can we use this trick to make automatic differentiation linear instead of quadratic? And the answer is, fortunately, yes. So here's what John did. he represents a list by a function from list to lists. And this is the main trick. If the representation of like the concatenation of two lists is the representation of this list, function composition, the representation of this other list. And then if you want to go back from a list represented as a function to a normal list, you just apply that list to the empty list. Okay? And if you use induction, but I promise I won't use expensive words, but you can prove by induction that this thing like works. And in fact, for people that like monads and monoids, this works for any monoid. And it even works for any monad, and then it's called the Yoneda and the co-Yoneda thing. So you probably have seen people use that in Haskell. So you can kind of like generalize this to monoids or to monads, and the same trick works. Now, once we can like replace concatenation with function composition, and we look at reverse, now you see that reverse becomes still recursive, and it really kind of accumulates the list as you go. And again, look at this. The longer the list is that you're reversing, the faster it goes, thanks to the magic of the JVM. I love that, right? So instead of reversing a list of 20 elements, you should reverse a list of 500 elements. It's much faster. It's like, it comes for free. Isn't that amazing? I don't know how this machine does it, right? It does more work in less time. It's like a 10x developer, right? It's just like, it's amazing. But anyway, trick is to represent a list as a function. Now, how does this apply to dual numbers? Who knows? Does it apply? Let's make let's bet. Let's put in some money. Who wants to bet that this applies to dual numbers or not? Come on, people. How much do I bet? Like $1? Anybody takes the bet? Okay, I'll have like, I feel generous tonight. I'll bet $1. I think that's $1. Is that like, 10,000 Swedish krona or something? So does this apply to dual numbers? It does, but we need a little bit more structure. And my apologies, just like we had monoids, we now need rings. So what is a ring? A ring is another mathematical structure that has two operations. It has addition and it has multiplication. And it's simple. They like addition and multiplication are associative, commutative, so you can turn them around, and multiplication distributes over addition. So A times B plus C is the same as A times B plus A times C. All right? We all know this. This is like, again, like elementary, every kind of like kid in kindergarten knows this. They don't know that it's called a ring, but it is a ring. Okay? So what we're going to do is we're going to use the fact that we are dealing with a ring to take this trick from lists, from monoids, and generalize it to rings. So this is what we did for lists. So we took a list and we represented it as a function. And again, this was the main trick. So now what we're going to do is let's look at the structure of our computation over dual numbers. So this is again like, the dual numbers, all the rules, but written as pairs, not in Scala, just to make it even more concise. And then the things that are marked in yellow is what the mathematicians call tangents. So that's the epsilon part. And the real part they call primal. So I've just marked them because I don't like expensive words, so let's color code, right? Color by numbers. I like that. It's like instead of using complicated words, let's use colors. So all the yellow bits here, you see that all I'm doing is on the right-hand side here, I'm adding a yellow thing multiplied by a constant. Here, the same thing. I'm adding two yellow things, but I multiply them by constants. And that's the kind of same thing here. I'm multiplying a yellow thing with a constant. Okay? So if I look at the grammar of what I'm doing here, is that I'm computing this tangent, and it's either a sum of a tangent with a primal, or it's a tangent with a primal. Doesn't that look very much like a list? It's like a list, right? List, and this is the tail of the list, and this is the head of the list. All right, and then there's also addition, because like, you know, these things are rings, so we don't have only multiplication, we also have addition. So I think this will work. Nobody took the bet, so I'll take my money back. It's going to work. And this is because like any, like here, like so rings are really nicer than monoids. I'll going to get like, you know, push this multivariate case on the stack for a while, because I first want to explore, like, you know, John uses trick using rings, and then we've seen like how easy it was to go from the single variable case to the multivariate case. So we'll leave that for now. All right, so let's see how we can represent. So John Hughes represented lists as functions. What we're going to do now is we're going to represent numbers as functions. Okay? So if I have a number, or any value from a ring, any ring, I can represent it by a function that takes two numbers and returns a number. And I need two parameters here because I have multiplication and addition. Right? For lists, we only had list concatenation, but here we have like multiplication and addition. So I need two parameters. So the representation of a plus b with these two numbers is the representation of a with r, and the representation of b with r, and then s. There's like, you know, should be two parentheses here. Multiplication is this, and then we don't really need that. If we multiply by a constant, it becomes this. All right, so this is how you represent numbers as functions. Isn't that beautiful? You didn't know that, right, before tonight, that you can represent numbers with functions. Any ring you can represent by a function like this. And when we do this, suddenly, just like in the list case, magically this thing that was quadratic becomes linear. It's so beautiful. And again, simple stuff, right? This is a paper from 1986. I didn't invent anything new. I just said, okay, look at this. This thing looks like a list a little bit, so we can apply this. So, backwards AD, this is what's called backwards AD when you do it as functions, backpropagation. Backpropagation is just John Hughes' trick of doing lists as functions reapplied to representing numbers as functions. Beautiful. Functional programming. As I said, if functional programming wins, it's in deep learning. And we represent functions, numbers as functions. But the grumpy cat smells that there's something wrong. Okay? So what's wrong? Let's see. Let's first implement this. And I'm going to kind of like, you know, use a slightly simpler approach here. I'm not going to do these two numbers because I'm just leaving addition for now. I just want to focus on the multiplication part because that's the important thing. So I'm just taking one parameter. So the tangent now takes one parameter, and it kind of like, you know, does this multiplication just like I showed you here. Right? You see here with addition, like I multiply by 1 here. So I do that here. And then when you do multiplication, you know, you have to multiply it by, like, you know, you get this swap. So you multiply this side by the real part there, and you multiply that side by the real part of the other side. So that's the kind of like swap that you have like whenever you do the product rule. So this is an implementation of like implementing numbers as functions. Okay, super simple. Everybody here could have written this code. Everybody could have invented things so far. Does this work? We want to do another bet? No? I thought I was like getting out rich here tonight, but you guys don't take it. Here's the thing, and this is the one time I will swear tonight. Is like, you know, if you represent lists as lists, you can share this list. Once I represent this list as a function, I can share the function, but when I call that function twice, even though the function is shared, the computation of that function is not shared. So if I have a, like, you know, this example here, let A's equal some U's giant list, and I concatenate them, now, you know, this, you hope that this thing is kind of like shared. But if I represent them as functions here, I get a function that represents that giant list, and then I compose them. Now this function is shared, but still when I apply this to a parameter, that function gets executed twice. And so really what Hugh's trick gave us is it made something quadratic linear, but now it shows up that, of course, this is what you expect. Now something else that was linear becomes quadratic. So we're just kind of like push the problem from one side of the carpet to the other. So let's see if we can come up with an example that is quadratic. And it's really simple. We take a list of size n, and we make n of them, and then we just append, like, you know, an element in the front. That you would expect that takes linear time. But again, if you do that, you see that because this first list is kind of like now evaluated n times, it will become quadratic. So, it's kind of sad, right? We thought we were going on the right track, but now, because we lost sharing, it's still quadratic. And this was the example that was important, right? This is the simplest neural network where there's like many layers, and each layer has only like one neuron. So all these layers, when you read about this, a fully connected network, it has this kind of structure where every output here is connected to every input. So this thing should work. Otherwise, we cannot use this technique for training neural networks. So let's kind of like see what happens here. So let's apply this naive dual numbers, this naive backpropagation on this example and see what happens. Now it's a beautiful curve. Look at this, how smooth. Like the JVM really loves exponential, like functions that take exponential time. Look at this. It's like smooth as butter. Okay, so if you really want your JVM, not your garbage collection, not to mess you up, write things that take exponential time. But this is really bad. So what can we do about this? So we've represented numbers by functions, but by doing that, we've lost sharing, and something that was linear becomes exponential. That's bad, right? It's even worse than something that was linear becoming quadratic. It's like now becomes exponential. Oh, goodness. What do we do? Anyone wants to take a bet? No? All right. Well, remember that we have a ring, and one of the things on the ring was distributivity. Look at it. Here, we represent multiplication as function application. So here you see that this function here is applied twice. But what we can do in a ring, instead of calling a function twice, or like, you know, multiplying twice and then adding the results, what we can do is we can combine the arguments first and then call the function once. So distributivity allows us to kind of like, you know, instead of kind of like combining the results of a function, we can combine the arguments of a function. And then we can call this function once. So this is the trick. This doesn't work for lists because like lists don't have enough structure. But if we have a ring, we can use this trick to kind of replace this, which caused exponential behavior, by this. And all we have to do is before we call that function, we have to kind of like accumulate all the arguments. We have to add them up and then call that function once. Okay, so this leaves now one implementation detail, is how do I know, how do I keep track of how many times this function is shared, right? Because we don't want to call this function each time. We want to only call it when all the kind of like uses of them have been kind of like, you know, have contributed that to this sum, and then we call that function once. So how do we do that? Well, fortunately, Facebook uses PHP, and one of the best things from PHP is it uses reference counting. So let's use reference counting to keep track of how many times this function is shared. So every time we use a value, we'll increase the reference count. And every time we're trying to call the backwards function, we'll decrease the reference count. And when the reference count is 0, we know that we're done. We'll take all the parameters that we have accumulated and call the function once. Yeah? Simple, right? It's like kindergarten coding. Really simple. So here it is. And again, there's many other ways to do this. You can, if you want to try this at home, again, like if you want to do different ways of sharing and you don't need to use reference counting, this was what I found the simplest thing. So let's just keep a reference count to get count how many times this expression is shared. And then on the way back, we just decrease the reference count, accumulate all the parameters, and call that function only once. And then hopefully, this exponential thing becomes nicely linear. So here's the code. It's as simple as this. So let's look at the addition here. A plus B. We increase the reference count of A, increase the reference count of B, because we're using both of these parameters. And then it's still the same thing. In the backwards pass, we just pass this thing here. Multiplication is exactly the same thing. The only trick that we need to do now, and I had to split the epsilon into backwards and epsilon just to factor out the common code. So this is the the code that does the this accumulation. So we have a mutable variable here that accumulates all the incoming values. And then if the reference count is less than 1, I'll just call backwards with the total value, and I will just reset everything to 0 just to clean everything up, so that once we have everything slushes down, everything is nicely set back to 0. And otherwise, I'll just decrease the reference count and return 0. All right? So again, I need a little bit of state. But again, we all love mutable state, right? We cannot live without mutable state. True? Yes. And so here, again, mutable state always saves the day. And so I love mutable state. But this code still looks simple, right? The only thing here is I have to deal with the reference counts, and then this is exactly what I told you. You have to get add up all the incoming parameters until you've seen them all, and then you just do the backwards pass. Really simple. Let's see if this works. Yep. Here's our example with that trivial neural network. And guess what? It goes here and then, it goes faster, but then it goes up again. But it's still linear, right? So this thing that was exponential is back to linear. Awesome. So what have we done? Well, all we have done is added some little bit of mutable state, back up these arguments before we call the function and then call the function once, instead of calling that function multiple times and then adding them up afterwards. And the reason we can do that is because we have a ring. And that was, again, you don't even need to know that we're having a ring. It's multiplication distributes over addition. That's kindergarten math. All right. As I promised, I also have to get rid of this addition. So here's the final version, where you see there's no addition, and now the backwards thing takes 2 parameters, just as I showed you a few slides before. This is all nicely tail recursive, except that the JVM doesn't support tail recursion. So if you really want to make this tail recursive, you have to use trampolines and all kind of crazy stuff. But this is all of the code that you need. So now we have proper backpropagation that works linear time. There's no quadratic, no exponential things. It's all very simple. I also promised you to show you the multivariate case. Remember, that's with multiple parameters. Well, again, just instead of computing a single number, have this list, and all the code is really the same. Yep, except that here I need to add this pair of name number to the list. Otherwise, it's all trivial. All right, and then for my neural network, I can do one kind of trick. when I told you, you know, once you take the derivative, you have to update the weights. Well, this thing here is computing the derivative, so why don't I kind of like add a little bit of extra state, since I like mutable state so much. So when we're going backwards and we reach a weight, I'm going to get like immediately update the weight, because I have the derivative there, I have the weight. Let me just kind of like mutate that value there, right there. All right? So just another kind of pinch of like, you know, mutable state to make things look even nicer. Now, if you look at what's going on here, it's like we've been threading around all these values through this computation, like this pair of values. And that reminds me of something what's called attribute grammars. So, and attribute grammars is something that Don Knuth invented in 1967. So again, it's like all kind of like old, simple, standard functional programming techniques that we're using here. So this is the summary of the talk. So we didn't use any category theory. We didn't talk about Hessians. We didn't talk about like, you know, partial derivatives. We didn't talk about like, you know, matrices. We didn't like none of that, right? Pure, simple, like elementary mathematics. We took dual numbers, and this was all that we required from dual numbers. We represented dual numbers as functions. Then we ran into a little bit of trouble. First, this was exponential, then this was quadratic. But we fixed everything by using the fact that multiplication distributes over addition. Right? And then we had to add some, like, sprinkle in some mutable state to do this reference counting. So again, that's the important part, right? Mutable state. Remember, you cannot make anything efficient without mutable state. So we did that, and then we kind of, you know, created backwards AD. And that's all this that you need to know to do like differentiation. Now, every function that you write that takes a dual number will automatically compute the derivative. And this program can be anything, right? We saw it like, you know, this Taylor sign, remember that uses while loops and assignments. It will just work. Thanks to the like the magic of like, you know, a little bit of mathematics and a little bit of imperative programming. All right. Now, there's a lot of things that I didn't talk about today. And here's this is a long, long list. Because in order to get like, you know, turn this differentiable programming, now we know how to differentiate functions by just like using dual numbers instead of floating point numbers. But there's a lot of other software engineering problems here. It's like, how do you like make sure that your results are reproducible? Because often these weights, or typically these weights are initialized randomly. Plus, you know, the way you order your training data, like, you know, that might change what the actual weights end up being. So maybe, like, you know, with one way of training, your distribution will look a little bit different than when you train it in a slightly different way. So how do you know that it's still kind of computing the same thing? How do you put all this stuff in version control? Now we don't put code in version control anymore because we don't have code. So should we put the training data in version control? How do we get like know how to track the provenance and lineage of the training data? Because maybe the training data was polluted and we have to change it, or there was a bug in the training data. So all these kind of things, how do you debug this stuff? How do you kind of retrain a neural net when the underlying, maybe the flowers, because of global warming, you know, the flowers suddenly grow bigger. So now this whole model doesn't work anymore because the features of the flowers have changed. How do I discover that, and how do I retrain this? So there's a whole bunch of questions. The nets can have bias because maybe I've only trained it with this kind of flower and not with that kind of flower. So there's a whole bunch of different, how do you optimize this stuff? Like, you know, how do you tune the performance? You cannot say, oh, let's do less memory allocation, or like here, let's make it quadratic because then the garbage collector like behaves well. How do we do all these things? So there's a whole bunch of things that I haven't talked about that are important to make this stuff real, but hopefully, you know, everybody agrees what I explained to you tonight was trivial, right? super trivial. Everybody now understands how to take derivatives. You didn't need any advanced math, just dual numbers, some little bit of assignments, and distributivity. Thank you. Was it trivial, Michael?
Totally. I do understand
Okay.
everything.
Good.
So I just
Thank you.
wonder, why did I quit programming? What the fuck? I did something wrong in my life. All right. Anyway, so we have food here. Erik will be here for a while. Not all night. We have to leave at 8:30, I think. And yeah. Take the opportunity to ask Erik some really good questions. You know, there is only good questions.
Of course, there's
yeah.
only good questions. Yes.
Yeah. There's nothing called bad questions or stupid questions. It's there's only stupid answers. So, right.
Oops, that puts a lot of pressure on me. Thanks.
Thank you, Erik. I really appreciate that you came back to Stockholm.
It was my pleasure.